Hello everyone. This is Dhanalakshmi, Assistant Professor from Triple Department of R&D Engineering College. In this session, I would like to discuss about power transistors, power BJTs, which is the first unit of our power electronics. BJT we all can be knowing, but as a signal level BJT we have learned. Now we will discuss about what is power BJT. BJT is bipolar junction transistor. In short, we will call it as a transistor. So it's a power transistor. There are three terminals available: collector, base, and emitter. So signal level transistor, it's a flow level where it can handle of low rating. Whereas when we go for power transistors, it should handle high power rating. So that's why we term that we named it as a power transistors. The term power stands for high power rating. It should be capable of handling high power. So here we see that usually the transistors we were using for amplifying, or it will be using as a switch. So and also it is a junction transistor designed to higher. When we say power transistor, it should handle high current and power. So that's why we say it is a power transistor. And when we take the classification of power transistor, there are four major classifications of transistor. One is BJT, MOSFET, IGBT, then SIT. So the first classification, as we discussed here, it is BJT. So in this session, we would like to discuss about power BJT. So power BJT, the BJT stands for bipolar junction transistor, which is capable of handling the bipolar. So as the name itself tells you, it's bipolar, holes and electrons. Right? The conduction is due to both the minority as well as the majority carrier. It can be used as a switch or as an amplifier. So the purpose of this is to use it as an amplifier or as a switch. When we use it as a switch, the aim of the switch is to turn and off amplifying circuits. We know already. So here, when we take BJT, we have two types here. One is NPN transistor, the other one is PNP transistor. So here we can see the symbol of NPN, and this is the symbol of PNP. And here we can always we used to have a confusion that how to mark that arrow in that emitter. So you can remember in this way. So if you say it is NPN, not pointing in, so the arrow should point outward. And similarly, if I say PNP, you can remember in this way, pointing in. So therefore, the arrow should be marked inside. And the same thing again, NPN and PNP transistor. And when we take BJT, it has large current handling and power handling capacity. It is having a large current and power handling capacity. And when we say power transistor, then compared to the normal BJT, when I say a signal level BJT transistor, normal transistor, and we are comparing with the normal transistor and the power BJT, power transistor. So when compared to normal level, the power transistor should be able to carry large current and should be capable of handling large power. Right? And in the off state, it should offer high resistance to it should offer high resistance, high voltage resistance, and similarly during on state, it should be capable of handling high current. So this is the thing we have to remember. So when we go for power BJT, it should be capable of handling high current and voltage. So here, when we see in the structure, one second. When we see in the structure here, you can see that there is a one more layer added here. Apart from this, you can see that this drift layer, right? So this drift layer is not there in the normal BJT or the signal level BJT. Where this is the additional layer we have in the power BJT, and only because of this layer we say the device is a power device, right? So when we take a normal BJT, that is a normal transistor, we don't have this drift layer. So when we had this layer, drift layer, when this drift layer is included here, we say this device is a power device. Now, because of this drift layer, it is having a capability of handling high current and voltage. So this drift layer is again, actually when you take here, you can see a normal N, P and N, right? NPN transistor. In addition to this, we have this drift layer N minus layer. It is a lightly doped N layer. Because of this drift layer, it becomes a power BJT where it can carry, where it can handle large current and high current and high voltage. Here we can see that. Now we will see how it is working, the modes of operation of BJT. So when we take modes of operation of BJT, it can be classified into four regions. You can segregate that into four regions. One is cutoff region, active region, quasi-saturation region, and hard saturation region. quasi-saturation region. One second. Yeah. Quasi-saturation region and hard saturation region. So we'll see how this, how these regions are going to work, and what makes what is the difference between these modes of operation, and then from how to, in the saturation region itself we have two. Yes, in the saturation region itself we have two. One is the quasi-saturation region, one is the hard saturation region, and we should find out the difference between what is quasi and hard saturation region. So here we can see that in active region, that is, sorry, in cutoff region, it will be whenever we want to operate the BJT as a switch, we should operate between the regions cutoff and saturation, because cutoff will be an off state. When we make device to off state, it will be in cutoff region, and when we make the device to be in on state, it should work in saturation region. So on and off, between on and off, when it is going to act as a switch, it should on and off the circuit. So on state, it will be in saturation, and in off state, it should be in cutoff region. And in between this, we have another state, which is the active region. Active region is we will operate the BJT in active region whenever we want to use the BJT as an amplifier. So when we're going to use the BJT as an amplifier, in that case, we can operate the BJT in active region. Or whenever we want to use it as a switch, we should operate the BJT between the regions cutoff and saturation region. So here we can see that the regions are there. So and how to operate BJT in cutoff or active or saturation. So whenever we want to operate the BJT in cutoff region, both the junctions, both the input and output junctions should be reverse bias. That is both base emitter and collector base junction. That is, here you can see that the base emitter junction, and here it is collector emitter junction. Both the junctions, if they are in reverse bias, then the BJT will be operating in cutoff region. And similarly, if the input junction, that is base emitter junction, is forward biased and collector emitter junction is reverse biased, then it will be operating in active region. And if both the junctions are forward biased, both the base emitter as well as the collector emitter junctions, if both the junctions are forward biased, they will be operated in saturation region. Right? So this is a category where we have, if both the junctions are reverse biased, cutoff region, both the junctions are forward biased, saturation region. If input junction, base emitter junction is reverse forward biased and collector emitter junction is reverse bias, then it is will be working in active region. So we'll go to the curve so that we can understand better. So here you can see that this is the. So here you can see that this is our hard saturation region. This is our quasi saturation region. This is our active region, and this is our cutoff region. Right. So the lower part, this lower part is going to be our cutoff region. So as I told you, cutoff region is the region where when you want to operate your switch in the off state, then we will be operating our BJT in cutoff region. And we want it whenever we want to turn on the device, or when we want to operate in the on state, then we will be operating in the saturation region. And when we want to operate the BJT as an amplifier, then we will be operating that BJT in active region. Here one difference, one unique point is there, that is the quasi and hard saturation. So we should know what is the difference between quasi and hard. Quasi is something like semi, which means that the saturation is not deep here. Right? In quasi saturation, here you can see that the saturation is not deep. So therefore, whenever you operate the device in when you operate the device at high frequency, that is the frequency, if I say 10 kilohertz, that is 10,000 hertz, which means that 10,000 times per second. On and off, I have to do 10,000 times per second. So therefore, when it is operated at a high frequency, the more often it should return back to the off state. So if it is an on state, that is in quasi, only if it is in quasi region, it can quickly return to the cutoff region. Right. So therefore, from the quasi region, it can quickly return to the cutoff region. This is what called as quasi saturation. That is, it is not a deep saturation. Whereas when you take the hard saturation, where the saturation is very deep, so it will take longer time to return back to the cutoff region. So for low frequency applications, we can operate in hard saturation, and for high frequency applications, we have to work it in quasi saturation. So quasi is on state and cutoff is off state, and in between active region will be our region where when you want to make the BJT as an amplifier, in that case we can operate the BJT in the active region. Thank you.